Okay, thank you very much. So I'm going to go over the linear coherent light source. Basically, it's a free electron laser, and I'll try and explain what a free electron laser is in a minute. But I'm going to talk a little bit about the free electron laser, what it does, why it's interesting, and also why it's interesting in particular to this audience in terms of the amount of data it's gathering, and also the need to transport that data to other sites, supercomputers, which can do some of the analysis. So this is the Stanford Linear Accelerator. It's 2 miles long. It's up in the hills behind us there. Originally had a copper pipe that ran from here to the other 2 miles, and electrons were accelerated down that pipe. The electrons reach the speed of light within about 9 feet. After that, they just gather mass, E equals mc squared, of course. By the time they get to the end, they're 20 million times heavier than when they started. This was used for various experiments looking at the properties of matter, properties of protons, the fact they're made up of quarks. But more recently, it's been turned into a different type of machine, where the middle section of the accelerator is actually accelerating the electrons, which then get to the far end, and then they're wiggled past magnets. And as they wiggle, they emit X-rays in the forward direction. And each wiggle and the next wiggle, they're coherent with one another. So what you get is an incredibly bright X-ray. So what I'd like to do, rather than kind of go through the details, is give a quick video of what goes on in the accelerator. So if you could turn the video on. I hope so. Oops. Yeah. So this was in 2009, the first generation accelerator. This was the first one ever built in the world at these very high energy X-rays. And it was powered by actually it's 2 miles long accelerator. This is the accelerator, it's 30 feet underground to prevent radiation or anything like that, for shielding. So this is part of it. And what we're beginning to see is things that you've never seen before. How electrons work, how chemical reactions work, how catalysis works, how electrons move through materials. It's really quite outstanding. Since this was built, 2 others have been built, one in Japan and one in Hamburg in Germany. And so now we're ready to take the next leap so that we're once again ahead of the game. So this one will be superconducting, not copper. So this stuff is cooled down to very close to absolute zero, where helium liquefies. And instead of getting 120 pulses a second, we've got 1 million pulses per second. So that means huge amounts of data. So you can turn it off now, thank you. All right. All right, so let's go on to the next slide. So this is how some of the experiments are done this way. So you've got the X-rays coming in here. Oh, darn. The X-rays coming in there, but before they come in, you actually, what we call pump the sample that you're looking at with an optical laser. So we excite it, so to speak. The X-ray, after it's been excited, the X-ray hits it, and we get a diffraction pattern. Diffraction pattern, you can imagine if you're standing in water up to your knees, maybe, and very, very smooth waves are coming by you, then they interfere with one another when they pass you, and you get this diffraction pattern. And from that diffraction pattern, we're able to gather how fat your knees are or whatever. So, but it's a very difficult reverse process. So then you change you actually increase the delay between when you pump the target and the X-rays. So then we get something like this. I think I can do this. Yeah. So this up here is the laser pumping the target. The beam comes through, and you get a shot of the thing. You unscramble that, and you see kind of a benzene ring. And then you keep increasing the delay, and you see you're taking a movie of the benzene ring as it basically is no longer a benzene ring. Okay. So another example is catalysis. And catalysis is incredibly important. All your cars have got a catalyst converter in it, which takes the initial gases that come out of the engine, hydrogen carbide, carbon monoxide, and nitrous oxides, and turns them into less destructive type of things like water and carbon monoxide. And basically, the gases go through a porous substrate coated with special precious metals such as platinum, and out the other end, you get these nice clean gases. But we can look at this, and so as you look at it, you see you start off like at time 0, and now you've got the 2 atoms of carbon monoxide and some other atoms also resting on the substrate. And as time goes on, 300 femtoseconds later, a femtosecond is 1 billionth of a millionth of a second. So 300 femtoseconds later, some other oxygen atoms get interested in this, and they start to get closer and closer, and eventually off drifts the carbon dioxide, and the carbon monoxide is gone. And this can be viewed by looking at these X-ray photographs that we're taking. So let's get to the data analysis. We've got incredibly high rep rate, up to a megapulse per second. And they're ultra-fast X-ray pulses, and they're used like flashes from a high-speed strobe lamp. And both data processing and scientific interpretation, you remember you have to reconstruct the waves as they interfere, as they come past your knees or whatever it is, to actually find out what the knees look like. So they're very demand-intensive on computational analysis. And then the other exciting thing, but certainly difficult thing, is that the data rates are going to increase enormously. So the experiments in the next generation, well, actually in the current generation, but we need fast feedback. In other words, you want to look at the data as it's come in, quickly look at it and decide, am I getting the results I expected? Is it working? Is there something incredibly exciting going on that I need to change the configuration? You want a 24/7 availability. I mean, an experimenter brings his team in, and he's here for 2 or 3 days, maybe a week. And if the accelerator is off for a lot of that time, he's out of luck. He has to wait for his next time he's signed up to work on the experiment. Also, the jobs that we need to submit can be very, very short. They don't have to run for very long because we want the results back from them very quickly. So this tends to be very disruptive for computers that very often simulate host simulations that can run for days. Storage and speed obviously are very important, although I will be talking more about the data transfer rates. And throughput between the storage and processing is very critical. And also we want to be able to change the code and then rerun it because we've found some problem that we want to look at in more detail. So this shows you the data flow. So you've got a detector that sees the diffraction of the X-rays. So you get the diffraction pattern there, the X-ray diffraction pattern. You put together multiple pulses to begin to see a very clear diffraction pattern. And then by reverse kind of engineering the diffraction pattern, you can look at the interpretation of the system structure that you're actually bombarding with the X-rays. What this means in detail is you've got a detector, that's the megapixel detector, which is generating up to a terabit byte per second. We're hoping, we've not proved though, that we can then reduce that data in a data reduction pipeline, probably by compressing the data. And so we'll wind up with 100 gigabit bytes per second, or roughly a terabit per second going to the fast storage. We want to get feedback from this in the order of within 1 second, so we can figure out whether things are going wrong or becoming very interesting. And then we get the longer term, we want feedback in terms of minutes, so we can determine what we want to do next. The data from the fast feedback goes to offline storage, which can be either on-site or off-site. Off-site would mean it's probably going to a high-performance computer somewhere else. So when I talk about the high-performance computers somewhere else, we're setting up agreements with Titan at Oak Ridge, Corey at the National Energy Research Scientific Computer System, which is at Berkeley, NERSC. And we need to, for some of the experiments that we were doing, we actually need to move the data from SLAC to these supercomputers to do the very heavy lifting of data analysis. So the requirement in the data transfer field is we're getting currently roughly 20 gigabits per second from SLAC to NERSC, the National Energy Research Scientific Computer in Berkeley. Hoping to get to, well, we're planning to get to 70 gigabits per second by 2019, and this is before LCLS-II comes on. Experiments will be increasing their efficiency and the networking will be improving. And then in 2020, LCLS-II gets first light. The data rate goes from 120 hertz to 1 megahertz. And so if we look at the data transfer needs, 2022-24, we begin to need a terabit per second. You can see here the LCLS requirements are in blue. Moore's law is in black. So we run into real serious questions as to how we're going to do this, how we're going to scale up and actually meet that requirement. And this, by the way, is assuming that we can actually do the compression by a factor of 10. If we can't, we're a factor of 100 in trouble. Various things we're doing. The red shows you the LCLS-II requirements. The blue shows you NERSC plans for how much data they can accept. SLAC plans, actually, will be 200 gigabits per second to ESNet, and then we're going to be increasing in 2024. We can actually increase before that if the experiments are incredibly successful and generate more data than we had actually expected. So data transfer requirements. Today, using existing equipment, we have some DTNs, which are at NERSC and at SLAC, DTN data transfer nodes, which are at NERSC and at SLAC, and there's Lustre file systems at both ends. And currently we have a 100 gigabit per second link between the two sites. By the end of this month, or actually probably by the end of March, we'll have 200 gigabits. And we've been using widely used tools such as BBCP and XRootD, and we're getting a roughly 55 gigabits per second. And we're trying to figure out whether or not we can go faster, because we were hoping, well, we could do 100 gigabits per second. We're not getting it, so we're trying to figure out whether or not it's at our end or is it the NERSC end. Our suspicion is, well, I shouldn't cast aspersions. I won't cast aspersions as to where I think it is. In addition to this, we're working with a startup called Zeta, and they provide a high-performance data transfer solution which consists of software and a transfer system reference design. It's very state-of-the-art, it's very efficient. In particular, the goals they're aiming at is to make this efficient, cheap, and scalable. And they've demonstrated over carefully selected demonstration hardware, and that's what I want to kind of talk about next. So this shows you two clusters. One cluster is here, the second cluster is there. Each cluster consists of data transfer nodes, which are in yellow, plus the you might refer to as the burst buffer, which is some Mellanox, there's the burst buffer, they're in orange, and then some Mellanox switches. The data goes from the sender, that machine, to Atlanta and gets looped back and comes back to SLAC. So now we have in one place the sender and receiver and a 5,000-mile link between them. So that's very nice for testing. And we're getting something like 80 gigabits per second. We're running over an ES link, running over the southern arc of ESNet to get it going. It's very space efficient. There's just 6 U's per cluster, including the switches. This shows you in a bit more detail. You can see the storage servers are there. They talk via EDR to a Mellanox at 100 gigabits per second to a Mellanox switch, which then talks to the data transfer nodes, which then talk to, this is 4 times 56 gigabits per second over FDR, and then that talks to, via Ethernet, with 4 times 25 gigabit per second interfaces, NIC cards in there, to another Mellanox switch, and then that goes out to the other cluster via ESNet. In addition, though, we can also loop it back locally, and rather than sending data, just have a 2 times 100 linked aggregate group between the 2 clusters. So we can test to make sure we can run at 200 gigabits per second. Okay, so this shows you what each of the NICs is seeing. You can see that each of the streams is very consistent. There's not a lot of burstiness between them. But this was just doing memory to memory. It's doing memory to memory over 200 gigabit per second Ethernet. So there's no storage involved. And you can see we repeated it here 3 times. And so that seems to work at 200 gigabits per second. There was no need for TCP, no need for exotic proprietary protocols. The network's not the problem in this case. The storage, on the other hand, file-to-file transfers are at the mercy of the back-end storage. Even with generous compute power, the best designed and implemented strategies cannot create any magic with a slow storage back-end. Well, apart from replicating it and spending a lot of money, which is not what we've got. So this is using XFF read performance with HSSDs in a file server, basically in a burst buffer, measured using the Unix FIO facility. And you can see that all of them are getting very consistent throughputs. This shows you the queue size of the data waiting to be sent, which is nice and full. You want it full so that as soon as it's finished sending its chunk of data, it can get another one out of the queue. And from that, we can get roughly 20 gigabytes per second. So on the other hand, if we look at the write performance, you can see, first of all, it's much more jittery. And also, instead of getting 800%, we're only getting 400%. And what's happened here is the queue size of the pending writes has just plummeted. And what that means is that instead of getting a very high performance, one only gets 10 gigabytes per second. So write's much slower than read. File systems can't keep the queue full. So the conclusion from that is the network's fine. No need for proprietary protocols. There's insufficient IOPS for write. Of course, we can always scale up and add more stuff to it, but that takes money. So today we're limited by 80 to 90 gigabits per second over the long link. We don't want to use that 100 gigabits that we have to Atlanta and back is shared by all of SLAC. So we actually deliberately limit ourselves to 80 gigabits per second, so we let the rest of the SLAC scientists do something useful. We've been working with local vendors, in particular Mellanox, but there are many others too. Arista, AIC, people like that. We've been using state-of-the-art components, and many of them have failed. And so one of the things is we need fast replacements. In one case, we had to wait 2 months to get the parts replaced. We use the fastest SSDs we can afford for write. The biggest are also the fastest, but also the most expensive. We noticed that that there's a 20% improvement, but 60% cost increase. And I've only shown you so far the XFS throughput. Once we kick in the parallel file system, which is actually using BGFS, which is actually for the test cases I'm talking about, which is from Germany, the BGFS reduces the performance by another 50% on what has already been reduced. Okay, so here's a demonstration that we did. You can see the SLAC up here on the right. Whoops. And then Atlanta down here. The red shows that we've lit up ESNet while we're transferring the data, over 50 gigabits per second. We're running here. This is showing you the graph of what's going on. You can see this was in about a year, just under a year ago. Started transferring here. And over a day, we were able to transmit, actually, under a day and a half, we were able to transmit a petabyte of data between and coming back. The impact upon ESNet was noticeable. Just our stuff alone took 1/3 of the total bandwidth or total utilization of ESNet during that time. You can see these were some tests we were making. Then we run solidly for the 1.5 days. So in summary, what's special? I think it's scalable. We can add more NIC cards. We can add more CPUs. We can, if we have multiple links, which we will have, we'll have 2 times 100 gigabits per second. We're able to use both links. And we can have more storage links as we can afford it and as they're needed. The power and space is very efficient. I mean, basically you saw it was just 6 U's, so it can't be using a lot of space. It is speaking in terms of this kind of stuff, low cost. It's probably a lot less than your Lamborghini, but still not much. It's HA tolerant to a loss of components. So if you lose a link or if you lose a NIC card, it doesn't, you lose performance, but it does not die and you have to restart again. It's storage tiering friendly. There's reference designs. It's easy to use and it's production ready. Somebody said we should come up with a future petabyte club. I don't think we'll ever do that. Okay, the future. We want to upgrade the border. That will happen spring of this year, 2 times 100 gigabit to ESNet. Then on to, instead of sending it to Atlanta and back, sending it just to NERSC. So that's only about a 4 millisecond round trip time. It should be much easier. But NERSC is a very special environment. It's a supercomputer. It's called Cori. It's hard to modify. You get what you get, and if you can't use it, you're out of luck. So, and the focus has been very different to what we need. Our data is what we call embarrassingly parallel. In other words, we don't care what's happening. It's one event. The one event is all we know about it. It doesn't have to talk to another event to figure out that there's a correlation. There's no MPI needed or anything like that. So, and also there's very little vector computing doesn't help, and the computer-intensive problems are not there between the various events that we're analyzing. It's not easy to use for cluster computing, such as some of the tools we're using, unless Cray supports supporting application, which is pretty unlikely. We're only one small fish in a big pool. Also, using the NERSC birth buffer is not easy from an application, but it's much easier than modifying the supercomputer itself. We could bypass the NERSC DTNs and go directly to the Cori nodes, but that requires all kinds of problems, especially for where we're trying to get very fast feedback to the experimenter. And also, I mean, the supercomputer has a life cycle of, I don't know what, 5 or 6 years from conception to actually when it is actually useful and it running. So the components tend to be a little bit behind the latest technology curve. We're looking to exceed a petabyte per day by SC 2018. Okay, and that's it. So any questions?